So I'm going to give an overview of the pilot line, but firstly, I kind of want to, these things don't happen overnight. So I just want to give a little bit of an intro to how this evolved, because it takes years really to kind of pull this together. And over the last, say, 2-3 years, we've been working very closely with the Commission to kind of define what a pilot line in photonics would look like, because photonics is in a real transition at the moment. I think it's in a great place because particularly, many applications, especially in the integrated photonics, it's moving into the domain of integrated electronics. So we see this merger, and that means there's a lot of work needs to be done on standardization, on the ecosystem, and you get that sense of when I'm talking. Very, very quickly, just to talk a little bit about our team here. So some of you may be familiar, but just maybe a lot of people are from the electronics world. The group here has been established, say, about 15 years now, and we've got fantastic facilities. I think one of the models, and actually it's kind of almost like an IMEC model, is bringing industry. For example, you might have an ASML in the front end. Well, we've got some very good companies on site, like Ficentech, a German company, and they install machines in here and work with us, sort of put engineers on site. So that's one of the important ingredients to be able to do this kind of thing. You don't just buy a machine and hope for the best and bring people in. You have to have the supplier working with you. And we have a number of those companies here. And actually, we have a lot of interest in companies coming here because they build machines, we develop processes, so everybody wins. Historically, we've been involved in pilot lines since 2016. We led a European-funded program called PIXEurope, and that was principally photonic packaging. And over the last 2 years, we had a lot of discussions with the Commission. What would a photonics pilot line in the broader sense look like? So lots of meetings in Brussels, and actually a lot of lobbying. And I will say the electronics side of the house, let me say, we're not so inclined to look at photonics. It's a niche area. We had to convince them that there's a real need. And as you start to see the opportunities that photonics can bring to electronics, power savings, bandwidth, latency, things like that, and performance, that has real benefits. So you can read some of the things here, but as much to say, we're global now. We work with lots of companies, and people are very interested in what we do, want to partner with us, and a key part of that is working with our equipment suppliers. So the markets are large. Very aware of that. Communications, AI. AI is really taking we're getting a lot of interest in getting involved in that, and it's a large part of our European pilot line now. It's built in there, so overlapping very much with the Nano IC, and especially the ASPIC pilot line in Fraunhofer. That's a more electronics packaging and integration pilot line, so we have very close collaborations there. But more, we see areas of growth in quantum, in medical and consumer type applications, and we work in all of those. Just to highlight one nice area, this is work we've done with IMEC recently and Medtronic, miniaturizing a cardiovascular diagnostic device based on silicon photonics. And again, silicon photonics has really brought photonics into the electronic CMOS world, and we have to follow the disciplines. A lot of photonics people previously would not know what a PDK is, but you have to use those terms and really standardize processes. So this can be manufactured. There's a lot of integration of packaging, lasers, micro-optics, and so forth. So we're really starting to see these applications grow, and we need to look beyond just developing prototypes, which what we did originally here at Tyndall. We're now looking at scaling and manufacturing, and that's very much what we're doing in the PIX Europe Pilot Line. Okay, so just a quick indication of the areas of opportunity. So for example, this technology, co-packaged optics, it's essentially bringing, for example, for data centers, where you have a pluggable photonic module, and then you have an electronic PCB board where the optical signal is brought in an optical fiber, it's converted to electronic. You tend to burn a lot of power, so it's actually bringing the photonics right close to the electronics. So it's co-packaging of photonic and electronic components. So that's proven to be a really massive growth area. For example, you can see the compound annual growth here. So it's essentially going from nothing last year to billions of euros over the next couple of years. And essentially it's following this trend of chiplet packaging. It was mentioned earlier with nano IC. So really, we're seeing a real strong trend in photonics now around chiplets. So for example, where you might have a pure electronic chiplet assembly where you'll have different node sizes coming from different foundries. They're all integrated onto an interposer, like a 2.5D or 3D interposer. In many cases, the photonic kind of chiplet is really where the data input and output can be, save a lot of power, has very good performance, bandwidth and latency and so forth. So for example, the receiver, transmitter will be a photonic based chiplet. So again, that's a trend we see. And many of the companies we work with are asking, how can we increase the number of optical channels? How can we go from tens, maybe to hundreds, possibly thousands, to really increase the bandwidth capability of this? And I'll get back to that in a second. So historically, what we're seeing is, I said we started out about, say, 10, maybe 15 years ago, looking at very standard photonic packages. You might have a single fiber, you might have a laser, some electronics in there. This is a sensor for aircraft, stress sensing. It's a fiber interrogator, butterfly package. What we're seeing now is a move to these types of very advanced packages. So this is a project we did with Intel Natera, where we're integrating onto the Intel EMIB platform. So it's an interposer, it's an organic type interposer, optical fiber. So again, it's not optical chiplet. So the optical basically receiver converts it to electrical, and then you have your electrical, in this case it's an FPGA. So you start to see this kind of electrical interposer, very complex, and in some cases we might have 20,000 electrical interconnects on that board. Some of them are RF, very high frequency. And looking at the optical fibers, in this case we've got about 70 optical fibers. They're asking, can we go to 700? Can we increase it? Can we go an order of magnitude? How do we do that? So for example, we're working in projects with DARPA to look at how we address this. There's real risks with some of these projects, but there's real opportunities to be able to address, the increase in optical bandwidth, for example. So you may have seen this, and I think the message here is the scale of these packages now. So this is from NVIDIA, and what you start to see is liquid cooling. So the power densities are enormous. So again, we have to look at thermal management. So that's another thing we have to take on board. You can see the actual silicon photonic chips in here in the overall system. This is an optical switch type of an arrangement, and you have many optical fibers coming in here with the pluggable connections and using micro optics. Well, actually in this case they do not do that as a fixed connection. We're working on pluggable connectors to be able to mimic what you do in the electrical world. So you're starting to see this transition from kind of historically bonded fibers using things like epoxies that were okay years ago. We have to start to go to a lot of processes that are more compatible, like solder attach, pluggable connectors, very large numbers of optical fiber interconnect, hundreds potentially, and possibly even more, that you would see in the electronic interconnect type world. So just a simple schematic here, just to show the kind of complexity. It's kind of a small kind of organic kind of a layout chart here, just to look at the different components when we look at building all of these very complex photonic type systems. So people tend to think of the optical, and one of the problems there is there's so many foundries. It's really nuts. We have many foundries. We've got indium phosphide, we have silicon, lithium niobate. They all have different optical mode sizes. The fibers aren't compatible. You might work with Global Foundries one day, or you're working with Tara Semiconductor. There's many different approaches in how they interface, for example, photonic optical fibers, micro optics. So it's really very complex. Then you start to look at the electrical, and I mentioned we're starting to see a massive increase in the number of electrical connections that we are asked to look at. So we're really starting to build a very strong electrical design team now as well. So design is absolutely critical. In many cases, for example, in silicon, there's no integrated source, a laser. So you have to look at how you do that. So there's been a lot of work done here on different types of integration methodologies to integrate sources into silicon. And then, as I said, heat is really important. And then the actual package, how you build out all that out. So essentially the message here is it's extremely complex, and there's been very little done about it. So it's a massive opportunity to really start to standardize it. So as I mentioned, The ecosystem is very fragmented, and kind of in a sense, what I'm trying to do here is set the scene. So this is the issue, and look for the opportunity. So between the design, so people tend to design. You might be a large company, you're vertically integrated, you can do all of this yourself. But if you're an SME, really you struggle. So which foundry do you use? So if we get chips from a particular foundry, it could cause potential issues in the way that the package is designed. The actual packaging, and then even the test is a problem as well. So being able to address all of this in a kind of an organized, kind of well coherent ecosystem is, so you can see where the pilot line needs to go. It needs to address this kind of problem. The other thing as well is that everything's out there. A lot of these solutions are already out there. It's actually just bringing them all together and starting to kind of get them organized. Now, of course, there's things we need to do to increase things like, the optical numbers of optical channels, being able to improve how we manufacture those and so forth. But, and actually you can see this outside in the cabinet. So before we might have a small photonic package. This is an optical switch. This is work we did with IMEC. This is typical, the size of many of the packages we're starting to see. Huge, needs a lot of thermal management, and thousands and thousands of electrical connections, and looking at hundreds of optical fibers. So really, really, very, very large. So a real opportunity, but obviously a real challenge. So when we set up PIXApp in 2016, we were looking at, moving beyond the TRL, the technology readiness level, where, for example, we can develop a prototype and look at the transition to scaling. And again, it's been able to kind of bridge the gap here. So that was really the motivation for the original pilot line. So in that particular case, we brought in a number of industrial partners and being able to, there was a number of companies, for example, in the Netherlands, is very, very strong in integrated photonics in, for example, in indium phosphide. Sylvester and the team from Eindhoven, Mike Schmidt there's a very good heritage there. So there was a number of Dutch companies working in that space, and we brought them in. And we also brought in Synopsys. At the time, it was Phoenix Software. They were subsequently bought by Synopsys. So recognizing that design is really, really critical to develop PDKs for everything we do. So really the motivation around the original pilot line was to develop standardized technology, standardized packaging. So, and that's actually often hard to do because people want to break the rules and be very custom. Well, you can't do it here. And I think we have to kind of encourage people to follow the rules as much as possible. But to be able to do that, they have to be trained and they have to be aware. So training then is very, very important. So educate people. And much like what Nano IC is doing, we're starting to do, formalize those training programs. And then the other thing is linking the ecosystem. So ensuring that the foundries, because one of the things, for example, when we were setting this up, well, maybe the chips come from the foundry. Are they all tested? So we're going to package untested chips. Who's going to test? And the foundry will, well, we don't have a test system for this, so we haven't been kind of pushed to, well, okay, well, we'll have to test. So we'll have to build a test system. There isn't a test system. So you start to look at this, and Eindhoven have done a lot of work in that. So we've always brought Sylvester and the team in to help us build those test capabilities. And again, there's a great opportunity. Ficantech, that packaging equipment company, are now making test systems. They're a partner in our pilot line. So another important part is that, you have all these partners, but where do you go? So we set up a gateway here at Tyndall, a single point of contact. So when I get onto PIX Europe, you'll see the principles and what we've done there. We've brought them in because one of the problems is it's distributed. Photonics by its very nature is very fragmented. You've got lots of materials, talk about lots of different foundry suppliers and so forth. So, one of the first discussions with the commission, my point was, we're going to have lots of partners. And that's, it's not just going to be one or two partners, lots of partners. And really this kind of model is being very successful, or pretty successful, can be enhanced, made better. But that was the motivation. And that was really the drive to set up PIX Europe. So again, we had a selection of technologies, standardized those, put them in PDKs, and we had open type packages where you could develop your chips, see if they're working pretty well. And then we have fairly standardized what we call gold box type packages. So those early stage packages I talked about before, not the very advanced big switch type systems that we're now looking at, we need to address. But we have partners who could scale. and we had suppliers, material suppliers. So that's really another thing we brought into this new pilot line. Even though they're not partners, we need that supply chain. So again, we can bring them business, and that's a real opportunity for them too. Okay, so historically, what we've done is we developed design rules. So really out of frustration, because we were getting chips, and I could show you pictures, we just couldn't package them. So we documented this, and we gave it out as a PDF. We still do it, but with Synopsys, then we brought this into a design environment. So there was a design rule checking and so forth, and it was a like you do, layout and electronic type IC. And with that, then people could design. For example, this is one of those test packages. I think this one actually is outside in the cabinet. You can see that, but it was enabling us to design and lay out things also with the tools, with the equipment, because often these machines are very bespoke. Like Fick and Tech develop packaging machines that are very bespoke. I'll give you an example. We're now working with a company in Switzerland, and they build machines to make watches, Swiss watches. Okay, they're now building packaging machines, starting to work with us. We have to kind of avoid that. So there's a specialization around the thing we're doing there, but it just shows you the industry in photonics is still moving into that, microelectronics world, and we have to kind of support that transition. Okay, so the other thing we've been doing, so building up to PIX Europe, is in Euro practice, we started to standardize different types of packages. So again, we brought in our optics. We started to standardize electronic chiplet packaging by developing standardized interposers. So we can get, not just pure optical packaging, but also electrical. And there's been fantastic work done here at Tyndall on heterogeneous integration, but people want it. People have to be able to use it. So we've made a standardized package. And we actually worked with a US fab foundry, AIM Photonics, in the US, and they have a PDK that enables their silicon to be open, so we can transfer print lasers from Tyndall into that platform. So again, it's a foundry that's working with us, and our PDK is matching their PDK, and we got packages. So as I said, we've got these standardized chips. So another thing we've done as well is that with the foundries, you've got this disconnect. So from a packaging perspective, we don't really care, what's inside the chip, but we very much care about the optical IOs and the electrical IOs. So with many foundries around the world, what we've developed are what we call these reference chips. So this is just one example from AIM in the US. We've also done them with IMEC and many other foundries, where you've got standardized interfaces, and these then can be used to validate a process. So for example, if somebody develops a new optical fiber or whatever it is, a micro lens, we know the performance of that chip. It's a gold standard. Or somebody wants to install a machine. So Fick and Tech now, we've made lots of these, we give them out, and Fick and Tech will use that to validate that the machine they've installed gives the performance that's required. And we've even started to make electrical reference chips. So looking at RF interconnect. So to bring in the signal to the IC, the package has to perform. And we know that, like, for example, daisy chains and so forth, also thermal. But again, these are very, very useful in, validating processes like this company here at OFC this year. They developed a new molded micro lens. We've got a reference chip that we know the performance that it should give, and we've been able to develop that. So all of these standardized technologies are really important to be able to bring into a pilot line. Standardization is the key. It's the key word. So in scaling, how do we scale? So one of the things we actually learned in the pilot line originally was we were very much looking forward, looking at industry. Okay, how do we help industry? So as I said, we've got different ways of engaging. We learned that. So some companies want to, basically, you develop the process and they take it in-house. Then we have some of our European partners, the SMEs, especially in the Netherlands. And then looking at the OSAT. So this is, again, these are the large scaling, tend to be in Asia. This is where there's a real opportunity in Europe, by the way. So this is something we're now starting to address in our new pilot line, the OSAT scaling. But the other thing we've identified is that supporting researchers in particular is very important, because often giving them the right direction in an early stage, if they're designing an IC or designing a PIC or looking at an application, ensuring that they have the full kind of way forward, the full kind of, route to scaling is very important. So, feeding in, for example, through Research Ireland or Horizon Europe, this is a really great way to, to look at exploiting your programs. So this is actually really important. So in shaping the new pilot line, this was also taken into account. So we had all these kind of, necessary conditions that we had to meet. And again, this was basically when we were helping the Commission to define the call for the Photonics pilot line. All of these parameters were fed in. And again, training, we built up a great expertise in training and how we address that. Hands-on is very important, really, really important. So being able to do hands-on training. And again, building different methodologies, for example, working with MIT and developing VR-based training. So again, they have fantastic techniques through their edX program. We've been working with them on that. So again, all of this has been kind of brought in to the pilot line. Okay, so this year we kicked off PIX Europe. It's a large investment. It's a 400 million euro program, gratefully supported also by, you must remember, by the member states. So the member states have, put their support in us, and so it's not just the European Commission that are providing that support. I won't read all of these points, but it kind of reflects what I've been talking about. So, building an open access, so that's really important. It's open access. We have to develop breakthrough technologies. It's not just provide a service. So we're also looking at, some fundamental developments in the pilot line, really to increase, obviously, it's for European competitiveness and etc. So I've been speaking about packaging, but another and very important next development is to bring all of this system together, this ecosystem together. So it's looking at all of the technologies. So really kind of like from chip to test and to reliability, and covering some fairly low TRLs as well. But really to look at developing the advanced prototypes and scaling to production. Now, it's RTO based. We don't have industrial partners in there. And again, that was a difficult thing to work on. But, we've got industrial partners now who are ready to start to work with us to take those technologies. And ultimately, what we're developing is advanced services within the pilot line. So we will offer those services. And training, of course, is very, very important. And then close collaboration with the design platform, which Sylvester spoke about earlier, and the competence centers. So we're already starting to work with them. So again, the whole design, chip, integration. So I talked about, for example, a laser on silicon, all of that stuff. Of course, the packaging, the test, and building systems, training, and operations. So that goes back to this gateway. So we're working with our partners particularly in Spain. So I would say the Spanish government were really pushing this at an early stage as well. So with our partner in Barcelona, ICFO, we're working with them around the kind of centralization of this. And I will say the main kind of partners that are driving this are ourselves here in Tyndall. We have the people in Eindhoven and the team in Barcelona, in ICFO. So that's really they're the main kind of drivers of this pilot line, with of course all our other partners, and they're listed here. So it really is a pan-European pilot line. There's a lot of collaboration, obviously, and it's quite difficult to do. And this is why this distributed nature of the pilot line is very important, and it has to be managed. And I'll talk about how we manage that and how we kind of manage it from a technical perspective as well. Okay, so just very briefly, you can see the layout of the work packages. So again, it's structured in such a way that we have different work packages. So you see the technical work packages, the design, the chips, making the chips in the foundries. IMEC, for example, and VTT in Finland are included there. We have Eindhoven working on the indium phosphide. Of course, we're managing the packaging, the test and reliability. We're looking after reliability, and the demonstrators. So the demonstrators I'll get on to in a second, because the demonstrators to prove the technology, but they also do another very important thing as well. And then, of course, there's a huge amount of equipment. It's amazing. We're getting some really cool pieces of equipment, things we couldn't dream of last year, are going to transform the kind of things we do. And then, obviously, we do the training and dissemination. So I get on to some of the operations thing in a second. And a little bit about what we're doing. So the operation of the pilot line is, it's into the future, but the grant period is running for 5 years. We started this year in June, so really pretty much just getting off the ground. But the idea is we start to engage with industry as early as we can. So one of the things we thought about is, okay, we're going to get all this equipment. We've got to tender for the equipment, and it's going to take time. That's going to take a long time. But we want to do things pretty quickly. So one of the things we're going to do is training, because we already do that. But we also have early release of technology. And I'll explain, for example, in packaging, how we're approaching that. Because I think industry would get frustrated if they said, well, we've got to wait for a couple of years. A couple of years in the semiconductor world is enormous. Typically an 18-month cycle is, you start to see things evolve over an 18-month period in the semiconductor domain, I believe. So, 3 or 4 years, it's too long. So we have to move quick. So, okay, so just very briefly from a technical point of view, covering a broad range of wavelengths. So going down to deep UV, right up to the mid-IR. So for example, with a Polish team, we're working in the mid-IR. There's a company called Vigo Photonics, doing a lot of work in that space. We have not done much there, but for sensing and diagnostics and kind of defense type applications, this area is very important. And of course then in communications, but it's not just communications. And some of the demonstrators we're developing will show that capability. So again, developing, historically in PIXApp, we were just doing this. Now, it's also worth mentioning there were other pilot lines. There was Impulse, which was very much around the chips. So, we have a head start and we know how to do this, but they were all developed independently. So, what we're doing here is merging all of these together. And we've got very nice examples of developing PDKs. We've just finished work on a glass interposer. We're developing a PDK for that glass. So how you lay out your routings, your vias, what the spacing needs to be so it doesn't crack. All of these kind of things are very, very important. We have a PDK around that. So it actually does really, come to something very, very important. And really, this is the interface with the pilot. This is how you interface. The majority. It's not kind of go in and see, all the fine details. We can do that, but it's really ideally, you don't, if you're looking to use a fab, you don't have to walk into the fab and see all the chemicals and so forth. And that's tends what happened historically in photonics, but to scale to mass markets, we have to use this type of approach. Of course, from a development point of view, we want to encourage that. And we have other programs like, the Research Ireland type activities as well. So that's where a lot of the deep tech research is also being done. So from a service point of view, we're standardizing everything. We have a gateway, so there's somewhere to contact with very experienced people. We're doing a number of chip runs. You can see the numbers here. This is what we put into our proposal, so we have to deliver. And we're developing standardized packaging runs as well. And really, the thing here is, and we're starting to get experience in this, you can have a packaging run for a communications device or a medical device, and it can be on the same platform. It can be on the same type of wafer if you design things properly. So you can start to mix and match and relatively quickly scale. And of course, then test and service, test and reliability services. So that's something we want to expand here quite a bit. There's been very little in reliability. If you ask people how reliable their devices are, they often don't know. And some of the materials are terrible, like epoxies. And we want to get epoxies out of a lot of this stuff as well. Okay, so for example, we have some brilliant machines already. They're in the labs next door, but they're pretty much manual and they're very much built around package type assembly processes. So without going into too much detail, we're starting to do a lot more on the surface of the wafer. If you look at a photonic chip, you're coupling to the edge. And, really, if you ask an electrical packaging person, they can't believe it. They're shocked. You're actually attaching fibers to the edge of a chip, and you're using epoxies to bond it. I've had these discussions. And really, when you hear that, you say, we've got to change this. So we're moving things to the surface. We're doing a lot of more surface optical coupling. There's a number of different approaches there. We're looking at 2D optical interfaces. So having arrays of pluggable optical fibers. So we can increase the density. I mentioned we need to look at how do we scale. So we've got techniques around micro-optics and different ways to couple from the surface, like evanescent coupling and so forth. So wafer level and very much automation. So the machines are going to be quite large. So that's a big challenge for us, and we need to get them in here soon. Now, again, we know many of these companies, so we know what we're looking for. But just going back to the packaging. So I mentioned about early release. So for example, we already do this kind of stuff, but we need to make it better. So one of the biggest problems we see in manufacturing is, for example, using epoxies. We need to eliminate an epoxy. It's slow, it's expensive, it's unreliable. So we're starting to introduce solder attachment processes. So now we're talking to some of those companies who build those machines and say, we want solder type assembly processes. So for example, that company in Switzerland, we have a project with them, independent of this, to develop a high-end, a high market value, solder-based packaging machine for space. So that suits their type of business operation. But again, if this can be scaled, now we're starting to be able to do solder attach. Do solder attach, now you can go to wafer level. So we're going to start to make these available over time, make them early release. What are the breakthroughs we're looking at? So we're moving to hundreds, possibly thousands of optical interconnect on a chip. So looking at an order of magnitude. And we have ways of doing that. So we're starting to talk to companies like Corning, for example, using glass materials. And there's a number of, as I mentioned, the PIX pilot line in Fraunhofer. We need to increase the numbers of electrical interconnects. So going to thousands of interconnects. So again, a 10x increase there. And looking at more surface, wafer level, but really another very important area is models. So developing models. So looking, for example, like a digital twin of a package. So when you change the material, how does it change the performance of the electrical, if it's a more sustainable material. So building these very advanced models is something we're looking at. So we're building out a new team here to build more accurate models, multi-physics models. So when you look at the optical parameters, how does that affect the electrical if you change the shape of the package or whatever? So again, this is something very, very exciting. We've been speaking to some of the companies like Synopsys to kind of help work with us on that. And this links into sustainability. So if you're looking at swapping out materials, how does it change the performance? And another important thing is cost models. So something we learned before working with MIT is they had very good cost models. We're bringing that in here as well. So something, to enable companies that they make the right choice in advance of, trial and error. So to make sure that the economics of the scaling. So we have a lot of experience in this. So just very briefly, you can see here the design flow. This is a glass interposer, the process sequence and so forth. Working with the foundries, so laying out the chips and so forth to seamless transition into the packaging. This is a Photonics machine. We've reconfigured it so it can do packaging on glass interposers. We need to move to wafer level. So again, optimizing the machine. This is work we've done with Sylvester and the team here, test systems. So this is a new glass BGA package. This is going to be brought into the pilot line and scaled up. But this test machine is built on BGA. It's an electronics domain. You wouldn't have typically seen that type of package really at all in photonics. So now we're moving into more electronic style packaging. We've built a full test system. And again, this is a company, Photonics. They're going to start to manufacture that. So you can see immediate benefits to industry, even though they're not involved in the pilot line itself. So again, very briefly, we have our gateway, and that's the main mechanism of working with the pilot line. So it's between ourselves and in Barcelona. Probably set up the gateway in Barcelona, but we will be very strongly involved there as well, based on our previous history. Okay, so I'm getting to the end of the presentation, but just go back here. So I mentioned about the gateway and how this operates, because we have a lot of partners. So one of the things we've learned previously, very successfully to implement is demonstrators. So the demonstrators, in some cases, I describe them like a concept car. You're never going to drive the car, but it shows all the different things you can do. And really, we've picked a number of demonstrators in medical, in communications, in AI, and so forth. So you can start to see some of the features here. And we've identified different partners. So it validates the technology, but the other thing it does is it's a pipe cleaner for this system of how you operate, the supply chain, which is kind of cool. So really, that demonstrator is not, as I say, is not just technical, it's also operational. And that's something we're managing. And it's based on previous experience. So I mentioned previously in our PIX Europe Pilot Line, we developed a very successful silicon photonic based transmitter. So you can see here the actual silicon photonic chip. This was fabricated by IMEC. There's lots of micro optics in it, RF and so forth, ceramic interposers, etc. But again, being able to do this and being able to coordinate different partners, is very, very important. And it's something that's necessary in photonics. And I think over time there will be some level of consolidation and it'll make things easier. But it's very distributed. That's the challenge we face, particularly in the photonics world. So again, you know, this is PIX Europe, but linking in with the design platform and also the competence centers in terms of design standards, design kits. We know the team there very well, Sylvester and Romano. But also the training courses, so we're setting those up. We'll get onto that very briefly. We're also starting to work with some of the pilot lines like PIX in Fraunhofer, because there's a compatibility there. So we're going to have a joint pilot line day fairly soon in Brussels and start to kind of work together around that. Just very briefly on our training. So there's lots of training programs. We've done training, you know, a lot of training over the years. Very much on the lower TRL. So we're focusing here much more on manufacturing. So for example, with those machines that are coming in, what we want to be able to do is people come in and see how they operate. So actually work on those machines with us. So it's very much around production. And I think that's what's really important. But again, we have a lot of experience around day courses. So for example, we have a 3-day training course where you come from anywhere in Europe. We have people come from the US as well. We actually have a queue for people to come to the training. But we break them up into small groups, move them around. So you might have 10 people or so. We break them into 3 or 4 groups and they move around. And they really get a very practical hands-on training. The interesting thing is they're usually not people involved in direct packaging, for example, but they want to know when they're designing something, what do I need to take into account? The other very important thing is you usually end up doing projects with the people that come. So it builds those partnerships. So training is much more beyond the training. It's partnership building, and I think that's very, very important. Okay, so just to summarize, it's a distributed pilot line. I kind of wanted to emphasize the history because I think that's really, really important. So the pilot lines didn't just appear out of nowhere. You know, we saw the problem. We started working it. The commission said, hey guys, what should we do? How do we want to frame this? We built that up over time. So as I said, it's built on significant experience of operating a complex thing like a pilot line. We're addressing the complete technology chain, and there's a real focus on the design standardization, and that means very close collaboration with the design platform. A strong focus on wafer level and automated processing, which I think is very, very important for photonics to scale. Yeah, comprehensive training program, which really links into the competence centers. So thanks very much.